There we go. So we talked about the simpler attractors. Let's now talk about kind of the more complex idea of chaotic attractors. The essential difference is that if you have something like a quasi, even something as perhaps complex as this quasi-periodic rotation of the torus that I mentioned, if you have two initial conditions that are going around the torus, the dynamics is kind of defined by, so the pure rotation dynamics on the circle is theta 1 dot is equal to omega 1. And then in the other direction, so maybe this is theta 1. And let's say that this direction here is the theta 2. So if theta 2 dot is omega 2, then the solutions to these are theta 1 of t is theta 1 at time 0 plus omega 1 t. And then theta 2 of t, or rather, let me write this as follows. Theta 1, 2 is theta 1, 2, 0 plus omega 1, 2. All right, theta 1, 2, t. So if you subtract the theta 1 and theta 2, you're going to get the difference between the initial conditions, and then omega 1, 2, t, right? And so you basically see that the two initial conditions, as they go around, like they would on the circle, if they were rotating around with the same frequency, after a little bit of time, you would see them kind of the same distance from each other, using that arc distance that we mentioned before. Yeah, they wouldn't go very far from each other. That's the key point. When you have a chaotic attractor, it turns out that, or rather, to define a chaotic attractor, you're kind of defining it against this idea that quasi-periodic motion keeps the distances tight together. So what you're requiring is that the system has sensitive dependence on initial conditions. That's one of the crucial properties of chaotic dynamics. And that goes as follows. The critical part is that you have two numbers, an R that has to exist, R bigger than 0, and any delta bigger than 0, such that if you start from x0, I'm sorry, start from initial condition x0, and x0 minus x1, the distance x0 minus x1 is less than delta. So this is circle size delta. Then as these trajectories go, for some t bigger than 0, the distance between them is going to be bigger than r. This is very clear in this case because one of these trajectories went over here and one of these trajectories went over there, right? So the game is you're requesting that there is an r such that if you pick any delta, you'll find a nearby initial condition to x0. So within delta, such that at some time t, the two are separated more than r. All the initial conditions run away from each other. A quintessential example, and how chaos theory can be deployed to life is you have two people walking down the same street, and they reach a building, and the building is symmetrically positioned to the street. And since one of them is slightly left of the center and the other one is slightly right of the center, they go opposite sides. And they separate more than that r. So they started within any delta, but they separated more than that r. And now imagine that now they again go down the street, they meet another building, and again, take different paths. They're going to keep exponentially separating from each other. And one of them might find somebody in the coffee shop that they talk to, and the next day they are maybe working in the company that the person has started, and the other one finds a sport interest on the other side of the town, and their interests now drift apart, and that's chaos in life. But you see the point as to how what is the one of the requirements of chaotic dynamics is this sensitive dependence on initial conditions. And then we have another one that we already talked about a little bit. It's topological transitivity. Remember, our attractor had to have topological transitivity, but now we're going to define it slightly differently. We're going to say dynamical system with this flow ST is topologically transitive on an invariant set A, provided there is an initial condition, a point x0, such that the closure of the trajectory through x0 is the whole of A. What is a closure? So topologically, what you have is, let's go back to my example of the torus. So as I mentioned, there can be this trajectory that is quasi-periodic on it. It goes around and around and spins and spins again and goes around and around and around. And so obviously a trajectory on a torus, which is a two-dimensional object, is a one-dimensional object. It's embedded in the trajectory, right? That's a one-dimensional curve. But take any sequence of points on that curve. Remember that I mentioned that the dynamics is going to be dense. It's going to pass arbitrarily close to any point. What that means is that if you look at any given point on the torus, there is going to be a sequence of points that are going to sit on that trajectory that are going to converge to that point on the torus, even though it's not on the trajectory, because trajectory itself is dense. So the closure of the trajectory is the whole torus. So this definition of topological transitivity asks for a single trajectory starting from some x0, whose closure is the whole object A. Yeah. How is that connected with the previous definition? Remember, in the previous definition, we had something like this. We had something of this sort. That for any two sets U and V, there is a time ST, and STU intersection with V is not zero. Now, this definition here is topological mixing, not topological transitivity. For topological transitive mixing, this needs to be valid for every time bigger than some tau prescribed time. For topological transitivity, this needed to be valid for a single time. You needed to be able to transit from a set U to a set V using the dynamics, yes? So you take set U, it intersects set V at some time. Topological mixing means that has to be valid for every time bigger than some pre-specified time tau. So you kind of, once you intersect the set U, there is always a set V, there is always some part of U that lands in V. That's a much stronger condition. Yeah. But of course, it implies topological transitivity, because if you're intersecting at every time bigger than tau, then you're certainly intersecting at a single time. And you can almost see immediately why this is equal to topological transitivity. Because suppose it's not, then there is no trajectory such that there is, such that the closure is the whole set. So there are gaps, whatever closure you're taking. So the dynamics is not dense. And so whatever trajectory you take, you won't be able to reach some set. Yeah, not a single trajectory is going to be able to reach some set. So you almost see intuitively how the two definitions of topological transitivity, one of them requiring just this, without requiring to be valid for every single time, and this closure are one and the same. But the mixing, topological mixing, is stronger. That means that once, if you have two sets, U and V, the trajectory is going, the trajectories from here are kind of going around. But then, as time goes on, maybe this trajectory is going to pass through V. And that would, this is U, that would satisfy the condition. So that would satisfy the condition on topological transitivity, because I got a transit from here to there. But for mixing, at any time t bigger than tau, there is going to be a trajectory that starts in U and is at that moment t in V. You see the point of difference? So it's not just that, okay, I can get from one place to another. Some trajectory from U is always going to be over here at those later times. So mixing is a much more demanding requirement. All right. So topological mixing implies topological transitivity. I just explained this. There is even a stronger notion of mixing. If you think about measures at this point in time, think about just, measuring, for example, sets on a circle with their arc length, or measuring areas in a plane. So a measure is a mathematical object that assigns a number to a positive number or zero to a set, right? So this says that the measure of the intersection between U mapped forward by flow and V is equal to the measure of U times measure of V. Oh, this is even stronger, because it says not only that there is going to be a single trajectory there at any given time, but there is going to be a substantial measure of trajectories in that set mu of V, provided that U has a given measure. And so this notion of mixing, which is, we call it metric mixing, implies topological mixing. And now you can define a chaotic attractor, a dynamical system with a flow ST on state space M as a chaotic attractor A, provided its attractor is topologically transitive and has sensitive dependence on initial conditions. Why did I mention topological mixing? Because I want to take you to Lorentz attractor. Topological mixing implies sensitive dependence on initial conditions. I'm not going to prove that, but I'll post a reference that proves that. So it's enough to prove that the attractor has topological mixing in order to prove that it's chaotic. But of course, you can also prove that the attractor has mixing itself in this sense, measure preserving mixing, in order to prove topological mixing. And that's really used in proofs of dynamical systems with attractors like this. It took us, it took Lusata and Melbourne. It was a very substantial effort to prove that this set of equations, the Lorentz attractor, is indeed mixing. So that was proven only about 12 years ago. Lorentz attractor was discovered in 1963, but that's the way the chaoticity was proven for Lorentz attractor ultimately. Until then, we had, of course, a computer-assisted proof. What is interesting is that in order to prove that, they actually had to argue a non-existence of a Koopman eigenfunction, of a Koopman operator eigenfunction. So these notions of mixing are actually also related to spectral properties of the Koopman operator, and this is where we're going to leave it for now. So let me finish here.